Welcome to the Deep Dive, the show where we take a stack of sources, articles, and research and really distill them down into the most important nuggets of knowledge. And it's all custom tailored for you, our curious listener.
That's the plan.
Today, we're plunging into a topic that's absolutely fundamental if you're trying to navigate the cutting edge of artificial intelligence. We're talking about large language model evaluation and benchmarking.
Yeah, it's a big one. And it's getting more important all the time.
We're going to try and unpack this complex world of how we actually assess these powerful AI systems. We'll dive into the diverse methodologies, the metrics used to measure performance.
All the different ways people try to figure out how good these things are.
Exactly. And then we'll take a close look at the leading open weight models, seeing how they truly stack up against each other.
See who's leading the pack, so to speak.
Right. Our mission, to cut through the jargon, hopefully provide you with a clear, insightful understanding of what makes an LLM good, because that definition seems to be changing all the time.
It really is. It's
Yeah.
a moving target.
So get ready for, well, hopefully some surprising facts and maybe some aha moments that will fast-track your path to being truly well-informed in this incredibly dynamic field.
Absolutely. What's fascinating here, I think, is that as LLMs become more integrated into our everyday lives, understanding how they're judged is becoming just as important as knowing what they can do.
That makes sense.
It's not just about flashy demos you see online or, what's trending on social media. It's really about a rigorous scientific approach to truly understanding their capabilities and, crucially, ensuring their responsible development.
Okay, so let's start with that. Part one. The science of LLM evaluation, more than just talking. This might sound basic, but why is evaluation, at its very core, so incredibly essential? It must go way beyond just checking if the text sounds okay.
Oh, absolutely. Way beyond. The foundational principle is that assessing LLMs isn't just some technical exercise you tick off a list. It's a critical process for responsible AI development and deployment. First and foremost, we're talking about performance and capability assessment. I mean, the most fundamental goal has to be determining if a model actually excels at the tasks it's intended for.
Right. Does it do the job?
Exactly. Does it do the job? And how well? This means quantitatively measuring its proficiency across a whole range of core competencies. Things like, basic language understanding, fluent text generation, but also more complex stuff like summarization, translation, and maybe most importantly, nuanced reasoning.
Nuanced reasoning.
Yeah, and the surprising fact here is how many subtle weaknesses this kind of rigorous process can uncover, even in models that seem really robust on the surface.
So it's about verifying if it does what it's supposed to do and finding out exactly how well, maybe even finding the tiny cracks in the surface.
Precisely. This rigorous process, it reveals very specific strengths, maybe weaknesses you didn't expect, gaps in its knowledge, or even, logical inconsistencies that just wouldn't be obvious from casual use. So for developers, it's vital. It helps them verify their initial design specifications. It's almost like a quality control check.
Makes sense.
And equally important for you, the user, it helps you pick the right model for your specific application. You wouldn't use a hammer to drive a screw, right?
Right.
And the same idea applies here. Knowing its precise capabilities, and maybe just as importantly, where it falls short, is crucial for choosing the right LLM.
I'm curious about the ethical angle here. We hear so much about biases in AI. How does evaluation actually play into that? Making sure these tools are used safely, fairly.
Yeah, that's a hugely important dimension, and it's why evaluation is really paramount for responsible AI. You see, LLMs are trained on these vast amounts of internet data.
Huge amounts.
Yeah, enormous. And that data, well, it inevitably contains biases. It contains falsehoods and sometimes, frankly, pretty harmful content.
Unfortunately, yeah.
So evaluation is the systematic process we use to first identify and then hopefully mitigate these issues. We have to test for the model's tendency to generate biased output or toxic stuff or just factually incorrect information.
So you're actively looking for those problems.
Actively looking. This ethical dimension, it's about preventing the model from perpetuating societal inequalities, making sure it provides reliable information, and basically safeguarding users from harmful advice or content. It's about trying to build AI that works for everyone safely and ensuring it doesn't accidentally make things worse.
Okay, so with this market just exploding with new LLMs all the time, what does this evaluation process mean for comparing them? How do we even start to make sense of which one is better or better for what?
That brings us nicely to comparative benchmarking. In this super fast-paced, rapidly expanding market, standardized evaluation gives us an objective way to compare these different models.
Standardize is key there.
Absolutely. By putting multiple models through the exact same tasks, using the exact same metrics, researchers and organizations can create things like leaderboards
Right.
or performance indices.
Ah, okay. Like we see online.
Exactly. And the aha moment here, I think, is that these leaderboards provide objective apples-to-apples comparisons. They're really invaluable for informed decision-making, whether you're, say, choosing a model for a big enterprise application or picking one for a personal project, or even if you're doing academic research trying to push the field forward, it helps cut through the marketing hype.
And it's not just about picking the winner, right?
Yeah.
I'm guessing these evaluation insights must feed directly back into making the models themselves better over time.
You've hit on a really key point there. The insights we get from evaluation, they act as a primary driver of innovation. It's not just a report card.
Right.
By pinpointing exactly where a model excels or where it falls short, these results directly inform decisions about architectural modifications. They influence what kind of data goes into the next training run. They guide the development of new fine-tuning techniques.
So it's a feedback loop.
It's a powerful feedback loop, yeah.
Yeah.
It really accelerates progress and helps direct where future model development goes. It's how we keep pushing the boundaries of what these systems can actually do.
And finally, maybe the most important one for everyday users, building trust and transparency. Why is rigorous evaluation so critical for that?
Well, rigorous and transparent evaluation is absolutely essential for fostering trust. Trust among users, among stakeholders, the broader public, everyone.
Yeah, that makes sense.
By openly reporting a model's performance, and this is important, including its limitations and potential risks, developers can set realistic expectations.
Manage expectations.
Exactly. This transparency is really a cornerstone of responsible AI deployment. It builds confidence. It ensures that you, the user, understand the true capabilities, but also the constraints of the tools you're using. It's basically about being upfront and honest about what the AI can do, and maybe more importantly, what it cannot do reliably.
Okay, so now we understand why evaluation is so critical. You're probably wondering, so how exactly do they put these models through their paces? That's our next big question. Let's unpack this taxonomy of evaluation methodologies, different tools for different jobs. Can you break down the main approaches for us?
Absolutely.
Okay.
Because there isn't just one way to do it. A comprehensive evaluation strategy, it almost always combines diverse approaches. Each one has its own unique advantages and its own limitations too.
Right, yeah.
The choice really depends on the specific capability you're trying to measure, the scale you need to operate at, and the level of nuance required. Let's start with maybe the most common and scalable method, automated evaluation.
Okay, automated. I'm picturing lots of code, lots of numbers. Very efficient, I imagine.
Precisely. Automated evaluation uses algorithms to score a model's outputs against some kind of ground truth or reference.
Ground truth. What exactly is that?
Think of ground truth as like a predefined, definitively correct answer, or maybe a set of human-verified, high-quality examples that the model's output is measured against.
Okay, a gold standard.
Sort of, yeah. A gold standard for that specific test. It's fast, and it allows for rapid testing on thousands, even millions of data points. You feed the model a prompt, it spits out a response, and then an algorithm quantifies how similar that response is to the correct answer or the reference.
Sounds efficient. But what's the downside?
Well, while it's incredibly efficient, its key limitation is that it often struggles. It struggles to capture things like semantic nuance or creativity, or sometimes even the factual accuracy of a response, at least not in the way a human can. It's great for checking if the words are similar, but not always if the meaning or the intent is actually correct or appropriate.
Okay, so for that deeper insight, that nuance, we often need to bring humans into the picture, right? That's human-in-the-loop evaluation.
Correct. Human-in-the-loop evaluation is really considered the gold standard, especially for qualitative assessment. It involves actual human raters who meticulously look at and assess the model outputs.
Sounds expensive.
It is. Yes, it's definitely more costly and time-consuming in terms of resources. You can't just scale it up infinitely like you can with algorithms. But it's pretty much indispensable for understanding how well a model aligns with complex human values and expectations. Humans can pick up on subtleties like faint biases or maybe an inappropriate tone that algorithms currently just miss.
So what exactly are these human evaluators looking for when they're in the loop? What are the key dimensions they're assessing?
They look at several critical dimensions. Firstly, reliability and relevance. Basically, are the outputs factually accurate? Are they pertinent to the context of the conversation or prompt?
Makes sense.
Secondly, safety. Are they identifying any potentially harmful content? Anything violent, inappropriate, or maybe promoting dangerous acts?
Crucial.
Absolutely. Then there's fairness. Are they detecting biases, either subtle or overt, things that might perpetuate stereotypes or treat certain groups unfairly? They also look at social norms. Do the outputs respect diverse cultures? Do they adhere to broadly accepted social conventions?
So being culturally sensitive.
Exactly.
Hmm.
Next is exactness and fluency. This is about judging the linguistic finesse. Is the tone appropriate? Is the grammar correct? Does the text flow naturally?
The quality of the writing itself.
Right. And finally, intelligence and capability. This involves evaluating the depth of a model's responses. Can it handle multifaceted queries? Can it sustain a meaningful dialogue over several turns? It's really a holistic assessment that, well, no algorithm can fully replicate just yet.
That is incredibly thorough.
And the aha here, perhaps, is that human evaluation remains the ultimate arbiter. It decides whether an AI is truly good in a real-world, nuanced sense, beyond just the numbers.
Okay, incredibly thorough, but as you said, incredibly expensive and time-consuming. Is there some kind of compromise, a newer approach that tries to bridge that gap between automated scale and human nuance? I've heard people talk about LLM as a judge. What's that about?
That's spot on, and it's a really fascinating development in the field. In this approach, you actually use a powerful, state-of-the-art LLM to act as the judge and evaluate another model's output.
An AI judging another AI.
Exactly. The idea is that a very capable LLM can potentially automate the assessment of some of those qualitative attributes we just talked about. Things like coherence or helpfulness or maybe even safety at a scale and cost that would just be prohibitive if you were using only human evaluators.
Okay, that's clever. How does this LLM judge actually work in practice? Does it just give a score, or are there different methods?
Yeah, there are several implementation methods people are using. There's point-wise evaluation. That's where the judge model scores a single output based on some given criteria, like rate the helpfulness of this response on a scale of 1 to 5.
Yep.
Pretty simple.
Okay.
Then there's pairwise evaluation. Here, the judge is presented with 2 different outputs for the same prompt, and it's asked to decide which one is better. This pairwise comparison method is actually the basis for popular leaderboards like the Chatbot Arena.
Ah, okay. I've seen that.
Yeah, Chatbot Arena uses thousands of human votes in pairwise comparisons, but you can also use an LLM judge for this. The results are often translated into an ELO score, kind of like in chess rankings.
Interesting. And the third way?
The third main one is listwise evaluation. In this case, the judge model is given a list of multiple outputs, maybe 3 or 4, and it has to rank them from best to worst according to the criteria.
That seems really efficient for getting relative performance. But if an AI is judging another AI, isn't there a risk? How do we know it's not just reinforcing its own biases? Or maybe even creating new ones? Is there a danger of an echo chamber effect here?
That's a very perceptive question, and it's absolutely a concern. While LLM as a judge is promising, it's definitely not without its challenges. The judge model can indeed exhibit its own biases, the same biases it might have learned from its training data.
Right.
It can also be quite sensitive to the specific phrasing of the evaluation prompt you give it. And it might lack the deep domain expertise needed to accurately assess highly specialized content, say, in medicine or law.
So its judgment is only as good as the judge itself.
Fundamentally, yes. The quality of the evaluation is dependent on the capability and, frankly, the alignment of the judge model itself. And this creates a dynamic where organizations that have access to the most powerful and often proprietary closed models might possess a significant advantage, not just in building new models, but also in evaluating them more effectively than others.
That could skew the field.
It could. The aha, maybe, is that even our AI judges need to be judged, or at least carefully audited and understood.
So how do researchers and developers get around that, or at least account for it, to make sure the evaluations are still robust and meaningful?
Well, a really robust evaluation pipeline often employs a kind of tiered strategy. Developers might use LLM as a judge for broad, rapid feedback, maybe during the early stages of development when they need quick iteration cycles.
Okay, for speed.
Right. Then, they'd follow up with targeted human review for the most complex, nuanced, or critically important cases, areas where human judgment is just irreplaceable. Things like safety checks or very subtle bias detection.
The high-stakes stuff.
Exactly. And crucially, they'll often maintain a fixed, golden set of prompts. This is a meticulously vetted set of test cases that they run regularly. It's used for continuous testing to catch performance regressions, making sure the model doesn't unexpectedly get worse at something over time as they make other changes. It ensures consistency.
Okay, that makes sense. Speaking of consistency, how we prompt a model during testing can dramatically affect what we learn about its capabilities, right? Can you talk about the key contextual testing approaches?
Yes, the way you frame your prompt during evaluation significantly influences the results you get, and it reveals different facets of a model's capabilities. There are three primary contextual approaches people talk about.
Okay.
The first is zero-shot. In zero-shot evaluation, the model performs a task with absolutely no examples provided in the prompt. It's testing its intrinsic out-of-the-box generalization ability. Can it handle a completely new task type? It hasn't been explicitly shown before. It's essentially saying, here's a new kind of problem, figure it out.
Testing its raw intelligence, almost.
Kind of, yeah. Its ability to generalize. Then there's few-shot. Here, the model gets a small number of examples, maybe just one or two or three, within the prompt itself. This assesses its in-context learning ability. How well can it adapt and learn from the immediate context provided right there in the prompt? It's like giving it a quick mini tutorial just before the test.
Okay, learning on the fly.
Exactly. And finally, there's fine-tuned evaluation. In this case, the model is first trained, or fine-tuned, on a task-specific data set before it's even evaluated on that task. This measures its peak potential performance in a specialized domain after it's undergone dedicated optimization. It shows what the model can do when it's fully prepared and specialized for a specific job.
Got it. Zero shot, few shot, fine-tuned. Different ways to see what it can do under different conditions.
Okay, so we're going to put some numbers on this, especially for the automated systems. What are the core metrics they actually use? Let's get into the quantitative toolkit, core evaluation metrics. Can you start us off with perplexity? What does that measure, and how reliable is it really? Sure. Perplexity is one of the fundamental metrics, especially in model development. It basically measures how well a language model predicts a given sample of text. You could think of it as how surprised the model is by each word it encounters in the sequence.
Surprised.
Yeah, like if it sees a word it really didn't expect based on the preceding words, its surprise is high and perplexity goes up. A lower perplexity score means the model is less surprised. It indicates a better understanding of the language's statistical patterns and suggests it's more confident in its predictions about what word comes next.
So lower is better?
Lower is better for perplexity. You don't necessarily need to memorize the exact mathematical formula involving logarithms and probabilities. Just know that lower perplexity means better prediction of text flow.
Okay, but does that mean it's actually generating good text?
That's the critical distinction. While perplexity is useful for gauging the raw predictive ability of the underlying language model, it doesn't reliably correlate with the actual quality or the coherence, or especially the factual accuracy of the generated text. A model could have very low perplexity, be very good at predicting sequences of words, but still generate grammatically correct nonsense, or confidently state incorrect information. So perplexity is useful, but it's definitely not a standalone measure of overall intelligence or usefulness.
That's a really important caveat. Okay, what about BLEU? The Bilingual Evaluation Understudy Score. I know it came from machine translation originally, but it seems to be used much more broadly now, right?
That's right. BLEU was originally developed specifically for machine translation, but yes, it's now widely applied to many other text generation tasks, like summarization or even dialogue response generation.
How does it work?
It measures the overlap of n-grams between the model's output and one or more human reference texts.
N-grams?
Yeah, n-grams are just contiguous sequences of words, like the cat is a 2-gram or big gram. The cat sat is a 3-gram or trigram. BLEU looks at the overlap of these short phrases, usually up to 4 grams, between what the model generated and what the human references say. A higher BLEU score, usually ranging from 0 to 1 or sometimes 0 to 100, means there's greater similarity to the reference translations or texts. It's great for quick, quantitative comparisons between different models or different versions of the same model.
But it has limitations too, I assume.
Oh, definitely. Its crucial limitation is its reliance on exact n-gram matches. This means it can unfairly penalize creative phrasing or semantically equivalent sentences that just happen to use different words than the reference text.
So if it says the same thing differently, it gets a lower score?
Potentially, yes. A perfectly good, maybe even more fluent or creative answer might get a lower BLEU score simply because it doesn't match the specific wording of the reference. The aha is that a high BLEU score doesn't always mean a truly better answer in a human judgment sense, just one that's more lexically similar to the provided reference.
Got it. Similar words, not necessarily better meaning. What about Rouge? How does that differ from BLEU? I hear it's used a lot for summarization.
Yes. Rouge, which stands for Recall-Oriented Understudy for Gisting Evaluation, is primarily used for evaluating automatic summarization. Like BLU, it compares a model-generated text, the summary, to one or more human-written reference summaries.
But it's recall-oriented. What does that mean?
Right. Unlike BLEU, which is more precision-focused, did the model's n-grams appear in the reference. Rouge is recall-focused. This means it measures how many of the n-grams from the human reference summary actually appear in the model's generated summary.
So did the model capture the important stuff from the reference?
Exactly. It's looking for the presence of key information, key phrases, from the reference summary within the machine summary. So if you're summarizing a news article, Rouge helps tell you how much of the important stuff identified by a human summarizer the AI managed to capture.
Are there different types of Rouge?
Yes, there are several variants. Rouge N focuses on the overlap of n-grams, like Rouge 1 for unigrams, Rouge 2 for biggrams. Rouge YAL considers the longest common subsequence, which is more sensitive to sentence-level structure similarity rather than just exact phrase matches. Each captures slightly different aspects of content overlap.
Okay. Now, for tasks that feel more like classification problems, maybe certain types of question answering, we often see the F1 score mentioned. Can you explain that one?
Sure. The F1 score is a very common and robust metric, especially for tasks that can be framed as classification problems, like deciding if an answer is correct or incorrect, or identifying specific entities in text.
How does it work?
It cleverly combines two other important metrics, precision and recall. Precision measures how many of the items the model predicted as positive were actually positive. It's about avoiding false alarms or being accurate when you claim something.
Okay.
Recall, on the other hand, measures how many of the actual positive items the model managed to find or identify. It's about not missing anything important or being comprehensive.
So precision is about accuracy of prediction. Recall is about finding everything.
You got it. The F1 score calculates the harmonic mean of precision and recall. This gives you a single number that balances the two. It ensures the model isn't just, say, very precise but misses a lot of things, low recall, or finds everything but includes a lot of junk, low precision. It's particularly valuable when the cost of making a false positive error is very different from the cost of making a false negative error.
Balancing act. Got it. And finally, these next two sound really interesting because they try to address those semantic limitations we talked about with BLU and Rouge, Meteor and BERT score. How do they tackle meaning?
They do. They represent a significant step forward. Let's start with Meteor. It improves on BLU by explicitly considering synonymy and stemming.
Synonymy and stemming.
Yeah, so it understands that words like big and large are similar synonyms, or that running and ran are related forms of the same root word, stemming. By incorporating these linguistic features, Meteor aligns more closely with how humans actually judge the quality and similarity of translations or generated text. It understands variations in wording better than BLEU.
Okay, so it's smarter about word variations. What about BERT score? That sounds like it uses BERT.
Exactly. BERT score takes this concept of semantic similarity a significant step further. It leverages the power of contextual embeddings, typically from models like BERT or its relatives.
Contextual embeddings, those vector things.
Precisely. Instead of just comparing surface words or simple synonyms, BERT score computes the cosine similarity between the vector representations of the tokens, words or subwords, in the generated text and the reference text.
Okay, break that down. Cosine similarity of vectors.
Think of it like this. If you represent the meaning of each word or token as a point in a vast multi-dimensional space, that's what embeddings do. BERT score checks how close the meaning points from the generated text are to the meaning points in the reference text. It's measuring the similarity of the meaning vectors, not just the words themselves.
Wow.
This is incredibly powerful because it captures semantic meaning much more effectively than just looking at surface-level lexical overlap like BLOU or Rouge do.
Yeah.
The aha here is that evaluation metrics themselves are evolving. We're moving beyond simple word counting towards methods that try to genuinely understand if the AI is conveying the right meaning.
That's a brilliant evolution. Okay, we've covered the science of evaluation, the why, and the how. Now let's shift gears to the evolving landscape of LLM benchmarking, standardized tests, and their limits. This is where the models really go head-to-head to prove their capabilities, isn't it? What exactly makes a standard test, a benchmark?
Absolutely. Benchmarks are essentially the proving grounds. They're where models demonstrate their capabilities in a structured way, hopefully providing a level playing field for comparison. At its core, an LLM benchmark is a standardized framework designed to systematically assess a model's performance on specific predefined tasks.
What are the key pieces of a benchmark?
The core components usually include, first, a data set. This is a curated collection of inputs, like questions, prompts, or documents. And crucially, this data set should not have been used in the model's training data. That's key to avoiding that memorization problem we discussed.
Right, testing generalization, not memory.
Exactly. Second, a set of tasks. These are the specific actions the model needs to perform using the data set, like answer the questions, generating code based on descriptions, or summarizing the documents. Third, evaluation metrics. These are the quantitative measures used to score. The model's performance on the tasks could be accuracy, F1 score, BLUAU, Forget, or something more complex. And finally, a scoring mechanism. This defines exactly how those metrics are applied and aggregated to produce a final score for the model on the benchmark, often normalized to a common scale like 0 to 100 for easier comparison.
So the process seems straightforward enough. Present the tasks and data, collect the model's outputs, score them against the ground truth using the metrics. Simple in concept, maybe complex in practice.
Pretty much. That's the basic flow.
But the landscape of these benchmarks is huge and varied. Let's dive into the benchmark landscape, a categorical analysis to get a handle on what exactly is being tested. We've got a great overview in Table 2.1 in our source materials that can guide us.
Absolutely. The landscape is vast because LLMs have so many potential capabilities. Researchers have designed benchmarks to probe all sorts of different skills. Let's start with general knowledge and understanding.
Okay, the basics.
Sort of the foundation. Early benchmarks like GLUE and its more difficult successor Super GLUE were really important in establishing baselines for general natural language understanding, NLU. Then came MMLU, which stands for Massive Multitask Language Understanding. MMLU became critical because it assesses a model's broad academic and world knowledge across 57 diverse domains, things like history, mathematics, law, ethics, you name it.
57 domains, wow.
Yeah, it's really broad. There's also ARC, which assesses grade school level scientific reasoning, and Truthful QA, which specifically focuses on a model's ability to avoid common misconceptions and falsehoods it might have picked up from the internet. That's crucial for building trustworthy AI.
So not just knowing facts, but also being accurate and avoiding common errors. What about testing how models think logically? That category is common sense and advanced reasoning.
Yes. This category tries to probe their ability to reason, to go beyond just retrieving information. For instance, there's GSM-8K. This benchmark tests multi-step mathematical word problems, the kind you might get in grade school. It requires the model to actually break down the problem into logical steps and calculate the answer, not just guess.
Challenging.
Definitely. Then there's HelloSwag, which evaluates everyday common sense inference. It gives the model a context, like the start of a scenario, and asks it to choose the most plausible continuation or ending from several options. It tests its understanding of how the real world typically works.
Common sense, which is harder than it sounds for AI.
It really is. And there's also Juana Grande, which assesses pronoun resolution. This is a subtle but really important aspect of language understanding. It tests if the model can correctly figure out who he, she, or it refers to in a sentence, which often requires common sense reasoning about the context. These benchmarks really push models beyond simple pattern matching towards something more like logical processing.
Okay, and a very practical and increasingly important domain now. Coding and software engineering. What benchmarks test that?
This is a key area where LLMs are showing huge potential value. Human Evil is a well-known benchmark here. It evaluates the functional correctness of Python code that the model generates based on natural language descriptions, doc strings.
So does the code actually work?
Exactly. Does it pass the tests? MBPP, or mostly basic programming problems, does something similar, but often for slightly simpler problems, sometimes providing input-output examples.
But you mentioned something more advanced before.
Right. The really interesting one, especially for real-world application, is SWE Bench. SWE stands for software engineering. This benchmark tests a model's ability to resolve actual issues logged on GitHub.
Wow, real bug fixing.
Yeah, understanding a real code base, figuring out the bug described in the issue, and proposing a working code patch. Success here indicates a much higher level of practical software engineering skill, far beyond just generating isolated functions.
That's a massive leap from just writing a simple function. Okay, then there's instruction following and alignment. This sounds absolutely vital for making these models useful and safe in user interactions.
Absolutely critical. IHEVL, for instance, measures how well a model can follow explicit and often complex instructions given in a prompt. Can it handle multiple constraints? or follow a sequence of steps accurately.
Does it do what you ask it to do?
Basically, yeah, even when the instructions are tricky. And then there's Chatbot Arena, which we mentioned briefly before. It's unique because it relies solely on thousands of crowdsourced human preferences. People chat with two anonymous models side by side and vote for which one they prefer.
No automated metrics at all.
Nope. It yields an ELO score based purely on these human votes. This makes it a really strong signal of real-world user preference and how well a model aligns with human conversational expectations and helpfulness. The aha here is perhaps that the ultimate test for a chatbot isn't some score on an academic benchmark, but simply whether real people actually prefer interacting with it.
That makes a lot of sense. And for responsible deployment, we absolutely need to talk about safety and bias benchmarks.
Indeed, these are essential. BBQ, which stands for Bias Benchmark for QA, is specifically designed to probe for social biases across multiple dimensions, like age, gender, race, religion, within question-answering tasks. It checks if the model gives stereotypical or prejudiced answers.
Trying to catch bias before it causes harm.
Exactly. And real toxicity prompts evaluates how often a model generates toxic, offensive, or harmful language when given certain prompts, including prompts that are themselves non-toxic, to see if the model amplifies negativity. Identifying and mitigating these issues before models are widely deployed is a major focus.
And finally, just a quick mention on multimodality benchmarks.
Right. As models become multimodal, understanding images, audio, etc., we need benchmarks for that too. MMBench is one example. It specifically tests visual language capabilities with a diverse set of tasks that require the model to both understand an image and reason about it to answer a question or follow an instruction related to it. It highlights the move towards AI that can perceive and reason about the world through multiple senses, not just text.
So connecting the dots here, it really sounds like the community's priorities for benchmarking have shifted significantly as the models themselves have gotten more capable, from basic NLU towards much more challenging domains.
That's absolutely right. Early benchmarks like GLUE set important baselines. But as models quickly surpassed those early tests, the focus rapidly moved. It shifted towards evaluating more complex reasoning, like in GSMAK or MMLU, towards measuring real-world utility in areas like coding, SW-Bench, and towards critically important aspects like safety, real toxicity prompts, and alignment with human preferences, Chatbot Arena. It's this continuous push towards more comprehensive, more challenging, and more realistic assessments. We're always trying to find the next frontier, the next set of capabilities that models haven't quite conquered yet.
But for all their utility, these standardized tests, these benchmarks, they aren't perfect. They have flaws. In fact, you mentioned it's creating something of an arms race in the world of LLM evaluation. What are some of the inherent limitations we need to be aware of with current benchmarks?
They absolutely do have significant limitations, and it's crucial to understand them. Probably the most pervasive and worrying issue is data contamination.
Data contamination, you mean the test answers are in the training data?
Exactly that. It happens when a benchmark's test set the questions or prompts used for evaluation inadvertently gets included in the massive data sets used to pre-train the model.
Oh, no.
Yeah. If a model has effectively already seen the answers during its training phase, then getting a high score on that benchmark doesn't measure true generalization or understanding. It just measures memorization.
Like a student who got the exam paper beforehand.
Precisely. It completely undermines the whole point of the test, which is to see how well the model performs on unseen data. And this risk is actually increasing as these pre-training data sets become astronomically large, scraping more and more of the web, making it harder to guarantee that benchmark data stays clean.
That's a huge problem. What about this idea of benchmark saturation and overfitting? What happens when the LLMs just get too good at a specific test?
That's another major challenge. When LLMs become extremely powerful, they can saturate existing benchmarks. Saturation means they achieve scores at or even above estimated human performance levels on that specific test.
So everyone gets an A+.
Pretty much. And when that happens, the benchmark loses its ability to differentiate between the top-performing models. If all the best models score 95% plus MAT, the test isn't telling you much anymore about who is truly better. We saw this happen with GLU, for example, which led researchers to create the much harder Super GLUE benchmark to restore differentiation.
So the tests have to keep getting harder.
Exactly. This dynamic can also lead to a problem called teaching to the test, or overfitting to the benchmark. Models might get optimized specifically for the formats and quirks of popular benchmarks, achieving high scores there, but those gains might not translate effectively to real-world utility or general intelligence. They become good at playing the benchmark game, but not necessarily better at solving diverse, real problems.
And it also sounds like many of these benchmarks might have a somewhat narrow focus.
Yes, that's definitely true for many of them. A lot of benchmarks test very specific, isolated skills in controlled, often academic-style settings. For example, getting a high score on a multiple-choice question answering benchmark might not accurately predict how well that same model will perform in a complex, multi-turn, real-world application. Think about debugging a software project, or having a nuanced negotiation, or managing a long-term collaborative writing task. These require integrating multiple skills in dynamic ways that isolated benchmarks just don't capture.
Like testing if a doctor knows textbook facts versus if they can manage a complex real patient.
That's a great analogy. The isolated skill doesn't guarantee competence in the complex integrated task.
This all raises a really important question. What does the future hold for evaluation? How do we evolve beyond these limitations? Where is this arms race heading?
Well, the field is acutely aware of these limitations, and is rapidly moving towards more robust and more representative forms of assessment. One major trend is the development of holistic evaluation frameworks. A prime example is HALM, which stands for Holistic Evaluation of Language Models, developed at Stanford.
Holistic. How so?
Instead of just looking at accuracy on one or two tasks, HLM assesses models across a much wider array of metrics simultaneously. It looks at accuracy across many different scenarios, but also incorporates measures of robustness, how it performs under slight changes, fairness, bias, calibration, how well it knows what it doesn't know, and efficiency, how much compute it uses. The aha here is that we're moving towards needing a much more comprehensive, multifaceted view of an AI's overall utility and safety, rather than relying on just a single headline score from one benchmark.
A more complete picture. And then there's this really exciting idea you mentioned, agentic evaluation. That sounds like a big shift from static, single-turn tests.
It's a huge shift, and potentially where the most interesting developments are happening. Agentic evaluation moves beyond testing isolated skills. It aims to measure a model's ability to achieve complex, multi-step, real-world goals. It's about assessing the model as an agent that can act in an environment.
Like the SWE bench example.
Exactly. SW Bench, tasking models with resolving real GitHub issues, is a perfect example. These issues are messy. They require understanding existing code, maybe running tests, using tools like a code editor or a debugger, planning a sequence of actions, and interacting over multiple steps. Success on benchmarks like this tests the model's ability to use tools, navigate complex environments like a code base, understand long contexts, and execute multi-step plans. Performance here is arguably far more indicative of a model's practical utility in complex real-world workflows than, say, just generating a standalone function correctly.
It's testing what the model can do in a dynamic situation, not just what it knows.
Precisely. It's like judging a chef by tasting the multi-course meal they prepared, not just by quizzing them on individual ingredient properties.
So this continuous evolution, this arms race in benchmarking, where as soon as models master one set of tests, new, more challenging ones emerge. It really means a model's performance score needs context, doesn't it? Its age, the difficulty of the benchmark, its relevance to real tasks.
Absolutely. The hot benchmark of today, the one everyone is optimizing for, is often the solved problem of tomorrow. This constant pressure is also causing a bit of a split or maybe a specialization in the field. You see some models being heavily optimized for the challenging academic puzzle-like benchmarks, like MMLU or GSM-8K, which test broad knowledge and reasoning. And others are being optimized more toward demonstrating real-world utility and aligning with user preferences, which is where things like SW Bench or Chatbot Arena come in.
So different models might excel in different areas.
Increasingly so. A truly state-of-the-art model today, especially a large generalist one, probably needs to demonstrate a strong, balanced profile across these different types of evaluation. It's not just about winning one specific game anymore. It's about showing competence across a range of intelligences: academic, practical, conversational, and safe.
You've really set the stage beautifully for us. Now let's dive into the main event, an analytical review of leading open-weight models, the contenders. This is where we see how specific models are performing and specializing. We've got a fantastic overview in Table 3.1 in our sources that gives us an at-a-glance view of their comparative benchmark performance. We should note, NA means data wasn't available, and not all scores are directly comparable across different reports, but they definitely indicate the focus areas for each model. Let's start with Alibaba's Quinn series. What's their overall strategy?
Alibaba's Quinn team seems to have a very comprehensive strategy. They're actively developing both broad, general-purpose models and highly specialized ones, with particularly strong focus recently on coding capabilities. They appear to be pursuing excellence across the board, aiming to build models that are both strong generalists and powerful specialists in key areas.
Okay, comprehensive. Now here's where it gets really interesting. As you mentioned earlier, the architecture. What are some of their defining technical features, especially this mixture of experts approach?
Yeah, a defining feature of their larger models is the aggressive and effective use of the mixture of experts, or MoE architecture. Take a model like Qwen3 Coder 480B. It has a massive total parameter count, 480 billion parameters in that case, which sounds enormous.
Huge.
But here's the architectural magic. During inference, when the model is actually generating a response, it only activates a small subset of those parameters. For the 480B model, it's around 35 billion active parameters per inference.
So it only uses a fraction at a time.
Exactly. This keeps the computational cost of running the model, the inference cost, manageable. It makes it comparable in speed and resource usage to much smaller dense models where all parameters are active all the time. But it still benefits from the vast repository of knowledge encoded in that huge total parameter count.
That's clever.
It really is. Maybe is that it's like having access to an absolutely enormous library, but for each specific query you make, an intelligent router only pulls out the handful of highly relevant expert books you actually need. This makes it efficient while still being incredibly knowledgeable overall.
That's a great analogy. And they also have these thinking and non-thinking modes in some of their models. That sounds quite innovative.
Yes, that's another innovative aspect, particularly in their instruct-tune models. They've introduced this dual approach. The thinking mode is designed to engage in explicit, step-by-step reasoning. It literally outputs its chain of thought. This is ideal for complex tasks like solving math problems or generating complex code, where you might actually want the model to show its work so you can verify its logic.
See how it got the answer.
Precisely. The non-thinking mode, on the other hand, is optimized for providing rapid, direct responses, more suited for general conversation or simple Q&A, where speed and conciseness are often paramount. This allows users, or the system itself, to dynamically trade off between reasoning depth and latency, choosing the most appropriate mode for the task at hand. It's like having both a super fast calculator mode and a deep, reflective problem-solving mode within the same AI.
Very flexible. And their coder variants, you mentioned a strong focus on coding.
Yeah.
What makes those stand out beyond just generating code snippets?
Right, the Qwen Coder variants are purpose-built for serious software engineering tasks. They are trained on massive data sets containing a very high percentage of code, sometimes up to 70% code in their training mix. And they utilize advanced post-training techniques, things like code reinforcement learning, RL, and even long-horizon agent RL. Yeah, this specialized training goes way beyond simple code generation. It aims to imbue the models with genuine agentic capabilities. This enables them to tackle real-world software development workflows that involve planning sequences of actions, using tools like accessing files or running tests, and having multi-turn interactions with complex code bases. They're designed to function less like a code completion tool and more like a collaborative software engineering assistant that can understand and actively participate in your entire project lifecycle.
That sounds incredibly powerful. So how do these architectural choices and specializations translate into actual benchmark performance for the Qwen series?
They translate very well, particularly in their areas of focus. The Qwen3 Coder 480B, for example, achieves state-of-the-art results among open source models on those challenging agentic coding benchmarks like SWE Bench. Its performance was reported to be comparable even to very strong proprietary models like Anthropic's Claude Sonnet 4 on that specific task. That's a huge achievement for an open source model in such a complex domain.
Really impressive.
Definitely. And the Qwen 330B A3B Thinking 2507 model also shows exceptional strength, particularly in reasoning and coding, scoring a remarkable 85.0 on the AAME 25 math benchmark and 66.0 on LiveCode Bench v6. It often outperforms much larger models by meticulously reasoning through problems step by step in its thinking mode.
And the generalist model?
There are large generalists. The Qwen 3 235B A22B has also put up impressive numbers. It was reportedly outperforming even top-tier proprietary models like GPT 4.1 and Claude Opus 4 on the Artificial Analysis Intelligence Index at the time of reporting, indicating very strong broad capabilities across many general tasks.
Wow, Alibaba is clearly a major player. Now let's turn to Mistral AI and their specialized ecosystem. They seem to have carved out a really distinct niche, focusing heavily on efficiency and specialized models, often releasing a family of models for different tasks. Is that right?
That's absolutely right. Mistral AI has a distinct strategy. They focus on creating highly efficient, often smaller but very potent, specialized open-weight models. They frequently collaborate with other research groups or companies as well. Their approach isn't about building the single biggest model, but about achieving targeted excellence. They release a suite of tools, each tailored and optimized for specific jobs, rather than trying to make one monolithic model do everything perfectly. They aim to be the best in class at specific tasks, often prioritizing efficiency.
Masters of focus. What are some of their standout architectural specializations or model types that achieve this targeted excellence?
Okay, let's look at a few. Codestral 22B is a prime example. It's a powerful code generation model trained on over 80 programming languages. It's proficient in standard instruction-based code generation, but it's also noted for being particularly good at fill-in-the-middle, FIM tasks.
Fill in the middle.
Yeah, where the model is given the beginning and the end of a code block and needs to generate the code that goes in the middle. This makes it exceptionally well-suited for integration into integrated development environments, IDEs, for real-time code completion. You type a few lines, hit tab, and it intelligently fills in the rest of the function or block.
Very useful for developers.
Extremely. Then they have Devstral. Unlike Codestral, which is more about generation, Devstral is fine-tuned specifically for agentic coding. Its strength lies in its ability to use tools to explore, understand, and actively edit complex code bases to solve real-world software engineering problems. It's designed to act more like that coding agent we discussed, navigating and modifying projects.
So different tools for different coding needs. And they have specialized models for other domains too, right? I remember you mentioned Mastral. That small model seemed impressive.
Yes, Mastral 7B is a great example of their specialization strategy. It's a relatively small model, a specialized fine-tune of their foundational Mistral 7B model, but it's specifically optimized for mathematical reasoning and scientific problem solving. And despite its size, it's highly competitive on math benchmarks. They also have Magistral, which is their dedicated reasoning model. Interestingly, it's trained using a novel proprietary pipeline they call RLVR, reinforcement learning from vocabulary reward.
RLVR, how does that work?
The core idea, as described, is to avoid just distilling knowledge from other, perhaps larger reasoning models. Instead, RLVR helps the model teach itself to reason better by rewarding it specifically for generating vocabulary patterns and logical structures that are associated with good step-by-step reasoning processes. It represents a unique path to developing strong reasoning capabilities more organically, rather than just mimicking another AI.
That's a fascinating approach. And of course, the original Mistral 7B itself was a landmark model for efficiency, really putting them on the map initially.
It truly was. The Mistral 7B model established their reputation. It was a highly efficient 7.3 billion parameter model that famously outperformed the larger Llama 2 13B model on many benchmarks when it was released. This impressive efficiency-to-performance ratio was achieved through key architectural innovations. They used grouped query attention, GQA, which speeds up the attention mechanism during inference, and sliding window attention, SWA, which allows the model to handle very long contexts much more cost-effectively than standard attention mechanisms. These techniques let them pack impressive performance into a significantly smaller and faster computational footprint.
So how does all this specialization and efficiency show up in their benchmark results? Do these models really punch above their weight class, as they say?
They absolutely do. That's kind of Mistral's signature. For example, Devstral Small 1.1 achieved a score of 53.6% on the demanding SWB Bench Verified benchmark. This made it state-of-the-art for open models in its size class, specifically for agentic coding tasks. That's a huge win for a relatively compact model. Codestral 20D shows dominant performance on standard code generation benchmarks, scoring 81.1% on Human Evil and 34.0% on RepaBench. These scores outperform much larger models, like Codellama 70B, likely thanks to its specialized training data and its large 32,000 token context window, which helps it understand more surrounding code.
And Mastral.
Mastral 7B scored 56.6 on the challenging math benchmark. Again, highly competitive for a model of only 7 billion parameters in such a difficult reasoning domain. And even the base Mistral 7B Instruct model generally outperforms other 7B models on conversational benchmarks like MTBench, demonstrating its strong fine-tuning potential for building capable chatbots.
It's really amazing how much performance they manage to pack into these smaller, specialized models. Okay, next up, let's talk about Google's Gemma family. What's their strategic focus? I keep hearing they're pushing AI intelligence right to the very edge, onto devices.
That's precisely Google's strategic thrust with the Gemma models. It represents a concerted effort to bring high-performance AI capabilities into resource-constrained environments. The big focus is on efficiency for enabling sophisticated AI to run directly on device. Think smartphones, laptops, wearables, maybe even cars or smart home appliances, reducing the need for constant cloud connectivity.
Making AI local. And what about their architectural innovations? This concept of effective parameters in Gemma 3N sounds particularly intriguing.
The Gemma family is really defined by innovations geared towards achieving high performance with remarkable efficiency. Let's break it down. Gemma 2, which comes in 9B and 27B parameter sizes, are powerful, dense, text-to-text generalist models. They're trained on massive data sets, 8 trillion tokens for the 9B, 13 trillion for the 27B, leveraging Google's advanced TPU infrastructure, providing a very strong foundation.
Okay, those are the bigger ones. What about Gemma 3M?
Gemma 3N represents a significant leap, specifically designed for on-device AI. First, it's a multimodal model capable of processing not just text, but also audio and visual inputs, which is huge for on-device applications like real-time translation or understanding your surroundings.
Multimodal on the device.
Exactly. And its core innovation lies in extremely parameter-efficient design. This is where the concept of effective parameters comes in. For instance, the Gemma 3N E4B model has 8 billion raw parameters, but functionally operates with around 4 billion effective parameters during inference.
How do they achieve that reduction?
Through a couple of key architectural tricks. One is my former architecture, which stands for Matryoshka transformer. It allows the model to selectively activate only certain parameters or layers, depending on the task complexity or resource constraints, effectively reducing the computational load. The other is per-layer embedding, PLE caching. This technique cleverly offloads some parameters, particularly from the embedding layers from active memory, like RAM or GPU VRAM, onto slower storage, further reducing the memory footprint without a major hit to performance. The profound insight here, maybe the aha, is that Google is demonstrating concrete architectural paths to packing genuinely powerful, even multimodal AI onto the relatively tiny silicon chips found in our everyday devices.
That's some serious optimization wizardry for limited hardware. How do these innovations translate to benchmark performance, especially looking at that on-device capability?
The results are quite striking. Gemma 3N E4B achieved a landmark score of over 1,300 on Elmarina, which is a popular human preference benchmark, like Chatbot Arena. This made it the very first model under 10 billion parameters to cross that threshold.
A major milestone.
A major milestone, absolutely. It demonstrates that highly capable on-device models can now achieve performance levels that were previously reserved for much larger server-based systems. It really signals a potential shift towards genuinely useful AI that can run locally offline on the devices we carry around.
And the larger Gemma 2 models.
The Gemma 2 27B, being a strong generalist, performs well across a broad range of standard benchmarks. It scores a solid 75.2 on MMLU, 74.0% on GSM-8K for math problems, and 51.8% on human evil for code generation. As expected, it consistently outperforms its smaller 9B counterpart across these tests.
Very capable family of models. All right, let's switch gears and talk about Microsoft's Phi series. Their strategy seems quite different, focusing on quality over quantity in data to achieve high-fidelity reasoning, even with smaller models. How do they manage to get that kind of deep reasoning capability with relatively fewer parameters?
Microsoft's Phi series is indeed built on a distinct philosophy, that model quality isn't solely a function of sheer scale or parameter count, but can be significantly boosted by the quality of the training data. Their Phi-4 reasoning models, which are around 13 billion parameters and dense, are fine-tuned from a base Phi-4 checkpoint.
So the magic is in the fine-tuning data.
Largely, yes. Their specialization in reasoning is achieved by training these models on extremely high-quality, carefully curated data that they describe as textbook-like. Specifically, they use synthetic reasoning demonstrations, essentially. Perfect examples of step-by-step logical thinking, or chain-of-thought traces that are generated by a very powerful internal teacher model called O3 Mini in their papers.
So it learns from perfect examples.
Exactly. It's like teaching a student by providing them with flawless, perfectly worked out solutions to complex problems, showing every logical step, rather than just giving them raw facts or messy real-world text. The plus variant of Phi-4 reasoning even undergoes additional outcome-based reinforcement learning to further refine its problem-solving abilities based on whether its final answers are correct. These models are explicitly designed to generate detailed, step-by-step reasoning chains before arriving at a final answer, effectively trading a bit of compute time during inference for higher accuracy and logical soundness.
So they're explicitly learning how to reason, showing their work, not just guessing the answer. What about their benchmark performance? Does this quality over quantity data strategy really pay off in the numbers?
The results strongly suggest it does. The 5-4 reasoning model showed dramatic improvements on reasoning-heavy benchmarks compared to their base models or other models of similar size. We're talking over 50 percentage point accuracy gains reported on challenging math benchmarks like ANI 2025 and OmniMath, and over 25 points on Live Code Bench for coding logic. These are truly impressive leaps in capability from fine-tuning.
Huge gains.
And remarkably, 5-4 Reasoning plus a score of 63.1% on the AIM 2025 math problems is comparable to the score achieved by the massive 671 billion parameter DeepSeek R1 model. This demonstrates exceptional parameter efficiency for complex reasoning tasks. The aha here is undeniable. Carefully crafted, high-quality synthetic data can sometimes be far more effective in boosting specific capabilities like reasoning than simply scaling up model size or using more raw, unfiltered data. Quality really can trump quantity here.
That's a huge return on investment for a relatively small model. Speaking of DeepSeek, let's move on to DeepSeek AI. They seem to be masters of a similar concept. Knowledge distillation for reasoning. How does their approach work?
They absolutely are masters of this, and it's a prime example of leveraging a powerful proprietary model to enhance an open one. DeepSeek AI uses knowledge distillation to create smaller, yet highly capable open-weight models specialized in reasoning. Their DeepSeek R10528 Qwen38B model is a perfect illustration.
Okay, so what's the base model and what's the distillation magic?
Interestingly, it's not a completely new architecture. It's actually a fine-tune of Alibaba's Open Qwen38B base model. The real innovation here lies entirely in the specialized fine-tuning data they used. DeepSeek employed its own state-of-the-art, very large proprietary reasoning model called DeepSeek R10528 to generate a large dataset of extremely high-quality chain-of-thought Hooty reasoning traces.
So very similar to Microsoft's approach using a powerful teacher model to generate perfect reasoning examples.
Exactly the same principle. They're essentially teaching the smaller, open Qwen38B model the sophisticated reasoning steps demonstrated by their much larger, smarter closed model. By training the smaller model on these expert demonstrations, they effectively distill the advanced reasoning capabilities of their massive proprietary model into an efficient, open 8 billion parameter package. This specializes the resulting model in complex reasoning, particularly in domains like mathematics and logic.
It's like bottling up the expertise of the giant model into a smaller, more accessible format.
That's a perfect way to put it. It's like a master chef providing incredibly detailed step-by-step recipe instructions to an apprentice, allowing the apprentice to produce gourmet-level dishes without needing decades of personal trial and error experience.
And does this distillation strategy pay off in the benchmarks for DeepSeek?
It pays off dramatically. The success is evident in the scores. The DeepSeek R10528 Qwen38B model achieves an astonishing 86.0 score on the AIM 2024 math benchmark. That's a staggering 10-point improvement over the original Qwen38B model is based on.
10 points is huge.
It's massive. And perhaps even more remarkably, this 8B distilled model matches the performance of the much, much larger Qwen3235B thinking model on this specific reasoning task. This result is a powerful testament to the effectiveness of high-quality data distillation for specializing models.
Okay, so this repeated success we're seeing both with Microsoft's 5.4 using O3 Mini and DeepSeek distilling from their R1 model, it really seems to signal a significant trend, doesn't it?
It absolutely does. It suggests that open-weight model performance, especially in specialized areas like reasoning, is increasingly becoming a reflection of the quality and capability of the proprietary teacher models used to generate their training or fine-tuning data. It seems the most effective path currently to creating a state-of-the-art open specialist model, in reasoning at least, is often to distill knowledge from a state-of-the-art closed generalist model. That's a profound insight into the current dynamics of the AI ecosystem.
That really changes how we might think about the relationship between open and closed models and the future of open source AI development. Okay, next up, Meta's Llama 3.3. What's their approach with this latest iteration? It sounds like iterative refinement is the name of the game for them.
That's a perfect description for Meta's strategy with the Llama series. They continue to build upon their immensely successful and influential Llama foundations. The focus seems to be squarely on iterative refinement and optimization, rather than making radical architectural changes with each release. They aim to deliver significant performance gains, often packaged into more efficient forms, by improving training techniques and data.
So building on success, what's new in Llama 3.3 specifically?
The Llama 3.370B model, for example, reportedly retains the same fundamental architecture as its predecessor, the Llama 3.170B. The key advancements seem to lie in the application of more advanced post-training techniques. These techniques are specifically designed to boost performance in complex domains that might have been relative weaknesses previously, such as advanced reasoning and mathematics, bringing the smaller model's capabilities closer to their much larger counterparts.
So the value proposition is getting more performance out of a smaller, more efficient footprint.
Exactly. The goal appears to be delivering performance that is comparable to their massive Llama 3.1405B model, but doing so within the significantly smaller, more computationally efficient, and thus more widely deployable 70B parameter package. It's about getting more intelligence bang for your compute buck by refining the training and alignment processes after the initial pre-training.
How does that look in terms of benchmarks or practical deployment readiness?
While specific numerical benchmark scores for Llama 3.3 weren't explicitly detailed in the source materials we reviewed, Meta's claim is that the Llama 3.3 70B model achieves performance on key evaluation benchmarks that is comparable to the much larger Llama 3.1405B model. That in itself is a significant achievement if borne out, showcasing impressive efficiency gains.
And practical deployment.
Its efficiency and suitability for practical deployment are highlighted by performance testing conducted on ARM Neoverse-based Google Axion CPUs. Reports indicated it could generate text at speeds comfortable for human readability, even when serving multiple users simultaneously on these CPU platforms. This really underscores its design focus on practical, scalable deployment in real-world scenarios, making it a potentially very valuable asset for businesses building applications on more accessible hardware.
Okay, practical and scalable. Let's talk about IBM's Granite series next. This one sounds like it's specifically tailored for the enterprise market, doesn't it? What makes Granite an enterprise-grade proposition?
Indeed. IBM's Granite series is explicitly positioned and tailored for enterprise deployment. The emphasis is squarely on practical performance, cost efficiency, reliability on common enterprise hardware infrastructure, and particularly strong capabilities in retrieval-augmented generation, or RGAG, which is crucial for many business use cases involving proprietary data. Their focus is on models that aren't just powerful in theory, but also robust, secure, governable, and cost-effective to operate within a typical business context.
What makes it technically enterprise-grade in its architecture and specialization? How do they achieve that practical efficiency businesses need?
The Granite 3.18B model is a dense 8 billion parameter architecture. It features a reasonably large 128,000 token context length, which is good for processing long documents, and it supports 12 languages, making it suitable for global enterprise environments. Its primary specialization, though, comes from heavy optimization for running efficiently in those environments. IBM, in collaboration with partners like Red Hat and Neural Magic, provides highly compressed and quantized versions of the Granite models.
Compressed and quantized. What does that do?
These techniques, like INTA quantization, or even more aggressive schemes like W4A16, 4-bit weights, 16-bit activations, dramatically reduce the model's memory footprint, how much RAM or VRAM it needs, and its disk storage size, sometimes by up to 3.3 times compared to the standard floating point version.
Significant savings.
Huge savings. And crucially, they also significantly improve inference speed, meaning the model responds faster, especially on common NVIDIA GPUs found in many enterprise data centers like the A6000 or L40 series. And they achieve this while maintaining approximately 99% of the original model's accuracy on standard benchmarks. The aha here is that enterprises can get almost the same high level of accuracy, but with significantly lower operational costs, less expensive hardware needed, lower energy consumption, higher throughput. That's a game changer for making AI adoption feasible at scale for many businesses.
Absolutely critical. And how does that specific focus show up in its benchmark performance? Is it all about proving that cost effectiveness doesn't sacrifice too much quality?
Exactly. Its evaluation reporting focuses heavily on those practical performance per dollar metrics that are highly relevant to enterprise IT departments. For instance, the quantized 8B Granite model scores 70.26 on the Open LLM leaderboard, which is nearly identical to the unquantized version's score of 70.30. This directly confirms that very little accuracy is lost during the quantization process.
Proof is in the numbers.
Right. More importantly, from a practical standpoint, the compressed versions demonstrate significantly better inference performance. Reports show up to 2.8x higher throughput, more requests handled per second, on common enterprise tasks like REG and code completion when running on the same hardware compared to the unquantized version. They also measured up to 2.7x lower latency, faster response time in single-stream use cases on a standard A5000 GPU. It's all about maximizing the useful work you can get out of your existing or planned hardware investments, making powerful AI much more accessible and economical for practical business applications.
That focus on total cost of ownership is definitely key for enterprise adoption. Now, let's look at Baidu's ERNIE 4.5. Their strategy seems to involve a strong focus on multimodality right from the very beginning, moving beyond just text processing.
That's correct. Baidu's ERNIE series of models, built on their proprietary Paddle Deep Learning framework, are particularly distinguished by their strong native focus on multimodality. This means they are designed from the ground up to understand and generate content across multiple data types, not just text, but also images and potentially audio and other formats. It's about deeply integrating these modalities, not just bolting on image understanding as an afterthought.
What's the architectural innovation behind ERNIE that enables this deep native multimodality?
The ERNIE 4.5 series employs a sophisticated multimodal heterogeneous mixture of experts, MO architecture. This innovative design features distinct sets of specialized expert subnetworks within the model. Some experts are specialized for processing textual data, while others are specialized for processing visual data.
Separate experts for text and vision.
Exactly. And crucially, these different types of experts are trained jointly, which allows the model to develop a deep cross-modal understanding. Information learned from images can directly inform text generation, and understanding text can help interpret images. The architecture uses techniques like modality-isolated routing to ensure that the text-specific experts and the vision-specific experts can specialize effectively on their own data types during training without interfering too much with each other's learning processes.
And the size.
The specific ERNIE 4.5 21B A3B model mentioned has 21 billion total parameters, but like other MOE models, it only activates a fraction, about 3 billion parameters for processing each token during inference. This makes it efficient enough to handle complex multimodal reasoning tasks.
So how does this unique architecture play out in its benchmark performance? What specific capabilities does it particularly enable?
While specific numerical benchmark scores for the ERNIE 4.5 21B A3B model weren't detailed exhaustively in our source materials, Baidu's documentation and announcements consistently emphasize that the ERNIE 4.5 series achieves state-of-the-art SOTA performance across a range of both text-based and multimodal benchmarks. Its key capabilities are particularly highlighted in areas requiring sophisticated visual understanding and complex cross-modal reasoning tasks, where the model needs to deeply integrate information from both text and images to arrive at an answer. The aha here is that these models aren't just adding vision capabilities on top of a text model. They seem to be fundamentally integrating these modalities at an architectural level, potentially leading to a richer, more grounded understanding of the world as represented in multiple data types.
A truly integrated approach. Finally, let's talk about Liquid AI's LFM2 model. This sounds like it represents a genuinely new paradigm, specifically targeting edge computing and pushing the boundaries of what very small models can achieve directly on a device.
It absolutely does seem to represent a different approach. Liquid AI appears to have a singular focus, creating small, yet remarkably capable, hyper-efficient models that are specifically designed for on-device and edge AI applications. In these scenarios, factors like extremely low latency, fast response time, the ability to run offline without cloud connectivity, and minimal memory usage are absolutely critical design constraints. The LFM2 model series represents a significant departure from the standard transformer architecture that dominates most other large language models today.
A departure. What's unique about its architecture, then? How does it achieve such extreme efficiency?
It utilizes a novel hybrid architecture. Instead of being a pure transformer, LFM2 combines blocks of different computational types. The sources mention it using 10 blocks of short-range convolution alongside 6 blocks of group query attention based on underlying principles from liquid time constant networks, a concept from other research involving differential equations in neural networks.
Convolutions and attention, that's different.
It is. This unique hybrid design is explicitly optimized for high performance, not just on high-end GPUs found in data centers, but specifically on the kinds of processors found in edge devices, CPUs, and dedicated neural processing units, NPUs. It's intended for applications running directly on devices like smartphones, industrial robots, autonomous vehicles, or embedded systems. Think about enabling complex tasks like on-device ORAG, retrieving and reasoning over local documents, real-time data extraction from sensors, or agentic control systems where constant cloud connectivity is simply not guaranteed, feasible, or desirable. The aha here is that they're building models from the ground up with the constraints and opportunities of edge computing in mind, aiming to excel where traditional larger LLMs often struggle right there on your local device, running efficiently without needing to constantly talk to the cloud.
That sounds incredibly important for bringing sophisticated AI into a whole new range of practical, real-world applications where cloud reliance is a barrier. How does LFM2 actually perform on benchmarks, given this unique focus and architecture?
The LFM2 models demonstrate truly remarkable parameter efficiency. The LFM2 1.2b model, with only 1.2 billion parameters, scores a respectable 55.23 on MMLU and an impressive 58.3% on GSM-8K for math reasoning. This level of performance is highly competitive with models like Qwen3 1.7b, despite LFM2 being nearly half the size, 47% smaller in terms of parameter count.
Wow, doing more with much less.
Exactly. And perhaps even more critically for its target applications, in terms of practical performance, LFM2 is reported to achieve up to 2 times faster inference speed on standard CPUs compared to equivalent-sized Qwen3 models. This speed advantage on common non-GPU hardware is a critical factor for enabling responsive and useful AI experiences directly on edge devices. It's really about delivering powerful AI capabilities efficiently and locally without needing that constant internet lifeline.
Wow. We've really gone through a whirlwind tour of these individual contenders and their strategies. Now, let's try to bring it all together in our final section. Synthesis and strategic recommendations. What this means for you. Looking across this complex and incredibly dynamic LLM landscape, what's the big picture takeaway? What major trends are emerging?
I think the biggest takeaway, the most fascinating thing here, is that the LLM landscape is clearly no longer just a monolithic pursuit of sheer scale, just building bigger and bigger models. It's rapidly maturing into a much more nuanced and diversified ecosystem. We're seeing the rise of specialized, highly efficient, and increasingly practical AI systems designed for specific purposes. You could almost call it the unbundling of intelligence.
The unbundling of intelligence. I really like that phrase. It suggests the idea of one single, all-knowing supermodel for every possible task is fading, replaced by a toolkit.
Exactly. That idea is giving way to a more sophisticated reality, an ecosystem of specialized tools. And this is reflected in the dominant architectural philosophies we're seeing emerge.
Okay, what are those dominant philosophies driving this evolution?
We can broadly identify 3 major currents. First, there's mixture of experts, MOE for scale. This seems to be the preferred path for achieving massive total parameter counts, often in the hundreds of billions, as seen with models from Alibaba's Qwen series and Baidu's Ernie. The MOE architecture allows them to encode vast amounts of knowledge while keeping inference costs manageable by activating only a relevant subset of experts per task. This approach seems geared towards creating top-tier general-purpose models with enormous breadth of knowledge.
Okay, MOE for the giants. What's the second philosophy?
Second, we have optimized dense models for specialization. This is arguably where the most vibrant innovation is happening right now, particularly in the open-weight space. It's exemplified by companies like Mistral, Microsoft with their Phi series, and the distilled models from DeepSeek. These efforts focus on creating highly performant models, typically in the 7 billion to perhaps 30 or 40 billion parameter range, much smaller than the MOE giants, but achieving state-of-the-art results in specific domains. They do this not through sheer size, but through meticulous data curation, high-quality synthetic data generation, knowledge distillation, and specialized fine-tuning for tasks like coding, mathematics, or logical reasoning. You could think of these as the highly trained sharpshooters of the AI world.
Specialized and efficient. And the third philosophy?
The third emerging stream is novel hybrids for the edge. This is being pushed aggressively by players like Liquid AI with their LFM2 and Google with Gemma 3N. These models employ new or significantly modified architectures, sometimes departing from the pure transformer paradigm, incorporating elements like convolutions or advanced parameter caching schemes. Their explicit goal is to maximize performance and efficiency, specifically within the tight resource constraints of edge computing environments running well on CPUs, mobile device NPUs, and other low-power hardware. They are enabling powerful AI capabilities locally on the device itself.
So these different architectural paths really reflect that unbundling of intelligence.
Precisely. The market is clearly moving past the notion of a single best model that reigns supreme across all tasks. Instead, we're seeing the development of a sophisticated ecosystem of diverse AI tools. And in this new landscape, the best model is increasingly becoming the best tool for the specific job you need to accomplish.
Okay, based on the performance and intended use cases we've discussed, can we informally group these leading models into some kind of performance tiers? Just to give our listeners a quick mental map or guide.
We can certainly try to group them based on where they currently seem to excel, keeping in mind this landscape changes rapidly. For Tier 1 reasoning, if your primary need is high-fidelity mathematical or complex logical problem-solving, models purpose-built for this, like Mistral's Magistral Small, Microsoft's 5.4 Reasoning Plus, and the distilled DeepSeek R1 Qwen 3.8b are arguably top contenders in the open space right now.
Okay, the reasoning specialists. What about coding?
For coding, we should probably differentiate. For Tier 1 agentic coding, where the AI needs to act like a software engineering partner, using tools, navigating code bases models like Alibaba's Qwen 3 Coder, especially the large ones, and Mistral's DevStral seem to lead the pack based on benchmarks like Celebi Bench. But for Tier 1 code generation, more focused on generating correct code from instructions or completing code in an IDE, Mistral's Codestral 22b appears to be a dominant performer, particularly strong on benchmarks like Human Evil and excellent for fill-in-the-middle tasks.
Got it. Specialized within coding itself. What about the edge?
For Tier 1 on-device edge performance, where resource constraints are paramount, Liquid AI's LFM2 1.2b stands out for its CPU and NPU efficiency and speed, while Google's Gemma 3 NDE 4b is currently the leader for bringing multimodal capabilities to this space with remarkable performance for its effective size.
And finally, the top generalists, the all-rounders.
For Tier 1 generalists, models that offer top-tier performance across a very wide range of tasks, the large MOE models like Alibaba's Qwen 3 235b, Meta's refined Llama 3.37D, achieving near 405B performance, and Google's Gemma 2 Twin 7B represent the current state-of-the-art among the open-weight options, providing a strong balance of capabilities.
That's a super helpful breakdown into these informal tiers. Now, this technical analysis is fascinating, but how does it translate into practical strategic guidance for our listeners? Let's talk about aligning model capabilities with application requirements, choosing the right tool. How should you, our listener, actually think about selecting the right model from this diverse landscape for your specific needs or projects?
Well, what's really fascinating, as you say, is how this deep technical analysis can directly inform practical strategic decisions. Selecting the right LLM today really means starting with a clear understanding of your specific application's requirements. You need to carefully balance the desired performance level on key tasks against factors like inference cost, how expensive it is to run, development time, ease of deployment, and the degree of specialization needed. It's a trade-off analysis. If you need an AI tool that can truly act as a software engineering partner, understanding complex repositories, suggesting and applying patches, interacting with build tools, basically doing agentic work, then models that excel on benchmarks like SW Bench are your prime candidates. Based on current data, that points towards Mistral's Distral or the large Qwen 3 coder models from Alibaba.
Okay, specific tools for specific complex jobs. What if the main focus is high-level scientific or mathematical research?
If your application centers on solving complex mathematical problems, conducting scientific simulations, or aiding in theoretical research where deep, accurate reasoning is the absolute priority, then you'd lean towards those specialized reasoning models. Candidates like Mistral's Magistral or Magistral Small or Microsoft's 5.4 Reasoning Plus have demonstrated state-of-the-art performance on challenging math benchmarks like Math and AIM, offering powerful analytical capabilities tailored for these domains.
Makes sense. And what about applications that absolutely must run locally on a device, perhaps without reliable internet access?
For on-device and edge applications where you face limitations on power, memory, and connectivity, the choice depends heavily on efficiency. Liquid AI's LFM2 emerges as a top choice if your primary concern is maximizing performance and speed on standard CPUs or NPUs. However, if your on-device application also requires multimodal capabilities, understanding images or audio locally, then Google's Gemma 3N is currently leading the pack, enabling rich, interactive AI experiences directly on the device.
Okay. Now, what if you need really powerful reasoning like those top-tier math models offer, but you're operating on a tight budget for API calls, maybe for a startup or an academic project?
That's where knowledge distillation really shines. For cost-effective, high-reasoning API calls, if you need the kind of mathematical reasoning power typically found in massive models but need to minimize your operational costs, a distilled model like the DeepSeek R1 Qwen 3.8b offers truly unparalleled value. As we saw, it provides the mathematical reasoning capabilities roughly equivalent to a model more than 20 times its size, which can drastically reduce your inference costs for accessing that level of high-end reasoning capability. It's a fantastic aha moment for getting top-tier intelligence efficiently.
Incredible value there. And lastly, for more common applications, like building a general-purpose chatbot or a retrieval-augmented generation RAG system, where cost is often a significant factor, but you still need solid performance.
For general-purpose chat and RGI on a budget, finding a strong, efficient all-rounder is usually the best strategy. The Mistral 7B Instruct model remains a highly popular and remarkably effective option, well known for its strong conversational abilities and excellent performance per parameter. Alternatively, if you need a bit more capability and have slightly more resources, choosing a mid-sized, dense model from series like Alibaba's Qwen 3, example the 8B or 14B variants, or Google's Gemma 2 family, like the 9B, can provide an excellent balance, giving you more horsepower without completely breaking the bank.
This really drives home the point about the diversity of the landscape and the importance of matching the tool to the task. So as we look towards the horizon, what are the future trajectories in LLM evaluation and development? Where are things heading beyond today's benchmarks and models?
The trends we've explored today, both in model development and the limitations of current evaluation methods, point toward some pretty clear future trajectories. The shortcomings of static benchmarks and the emergence of more agentic model capabilities are definitely setting the stage for the next generation of both AI and how we measure it.
So what will the next generation of evaluation look like?
I think we're moving decisively away from reliance on static, single-turn, often multiple-choice style tests. The next frontier of evaluation will almost certainly be defined by dynamic, multi-turn agentic benchmarks. These new benchmarks will be designed to assess a model's ability to achieve complex, real-world goals over extended interactions. They'll measure not just what the AI knows, but what it can actually do. Success will be defined by task completion rates in simulated or even real environments, requiring the AI to demonstrate planning, tool usage, understanding and processing feedback, and adapting its strategy over time. It's a much more practical, challenging, and ultimately more meaningful way to test true AI capability.
That sounds like a much more holistic and demanding way to measure intelligence. And this focus on task completion in an environment naturally leads to the rise of the system model, doesn't it? Evaluating the whole setup, not just the core LLM.
Absolutely. The focus of evaluation is bound to expand. We'll move from assessing a single LLM in isolation to assessing an entire integrated AI system. This includes the core LLM working in concert with potentially many other components. Retrieval databases for RAG, code interpreters for running generated code, web browsers for accessing real-time information, planning modules, and various other external APIs or tools. The LLM's performance will increasingly be judged by its ability to effectively orchestrate all these components successfully to achieve a user's complex, high-level objective. It's about evaluating the effectiveness of the entire team, not just the quarterback, and how well they collaborate to solve real problems.
This raises a really profound final question, though. The most advanced research, as hinted by the reinforcement learning techniques in models like Qwen 3 Coder and Mistral's Magistral, is pushing towards systems that can potentially learn and improve continuously through interaction with their environment and feedback. Self-improving systems. What does that imply for evaluation and safety? How do we even begin to measure or control something that's constantly evolving on its own?
That is the big question, isn't it? It creates an incredibly powerful potential feedback loop for capability improvement, but it also introduces profound challenges for evaluation, predictability, and safety. How do we reliably benchmark an AI system that is constantly changing, potentially adapting its behavior based on its interactions in ways we didn't explicitly program? How do we ensure that its self-improvement process remains robustly aligned with human values and intentions and doesn't drift off course into unexpected or undesirable territories?
Huge challenges.
Huge. Answering these questions, developing methods for evaluating and ensuring the safety of continuously learning, adaptive AI systems will likely be the central task, the grand challenge, for the next phase of LLM research and development. It's about building and understanding systems that can not only act, but also adapt and evolve, and crucially, ensuring that evolution is beneficial, remains predictable, and stays firmly under human control and aligned with our goals. The final aha, perhaps, is that the very nature of advanced AI is becoming more dynamic and autonomous, and our methods for understanding, evaluating, and guiding it must evolve just as rapidly to keep pace.
What an absolutely incredible journey we've been on today. We started by exploring the fundamental principles of why we even need to evaluate large language models, dove into the diverse methodologies and metrics used to do it, from automated scores to human judgment to AI judging AI, and then we took that deep analytical look at the leading open-weight models, unpacking their unique architectures, their specialized strategies, and how those translate into performance on this evolving landscape of benchmarks.
And I think the key takeaway is clear. The LLM landscape is no longer just a one-dimensional race for sheer scale. It's blossomed into this rich, diversified ecosystem. The concept of a single best model is fading. Now, best truly depends on the specific task at hand, the capabilities required, the efficiency needed, and the environment it needs to operate in.
You, our listener, should now be much better equipped to navigate this complex world, to cut through the hype, and to make more informed decisions about these incredibly powerful tools, whether you're using them, building with them, or just trying to understand their impact.
It's definitely a field moving at lightning speed. Staying informed about not just what the models can do, but how we measure their progress and their limitations is absolutely key to understanding where this technology is truly heading.
Absolutely. And that leads us to our final provocative thought for you to mull over. As these AI models continue to evolve, perhaps even towards forms of self-improvement, learning and adapting based on their interactions in ways we don't fully direct, how might our very definitions of intelligence, capability, and maybe even control need to change in response? What does it truly mean for us when our tools begin to evolve beyond our direct programming?
A deep question indeed.
Something to think about until our next deep dive.